Okay, let's dive right into this incredibly fascinating explainer on a cutting-edge autonomous intrusion detection system. And what's wild about this is that it literally treats network security like the physical fabric of space-time. Seriously, if you've ever felt like cybersecurity is just this exhausting, endless game of playing whack-a-mole with alerts, well, this system is going to completely change how you think about defending digital infrastructure. We're talking about a network that actually feels tension, warps under the pressure of an attack, and then autonomously turns itself to stoning to stop it.
Here's how we're going to break this down today. First, mapping the attack surface. Second, the holographic fabric metaphor. Third, tension, warp, and detection. Fourth, autonomous lockdown and recovery. And finally, number 5, proving the system actually works.
All right, let's jump straight into Section 1, mapping the attack surface and finding those fragile points. So, before we can even begin to defend a network, we absolutely have to figure out where its fragile points are. And crucially, we need to do this passively without firing a single active exploit or, setting off any internal alarms. Enter WNCDS, the Weak Node Classification and Detection System. You can basically think of this as the master cartographer of our security system. It passively discovers subdomains and calculates governance gaps using nothing but public data. It's constantly asking which nodes in a domain's public-facing surface are structurally underprotected. It doesn't hack anything. It just silently identifies the weak links where an attacker is most likely to kick off an island-hopping campaign.
Now, version 2.4.0 of WNCDS brought some major upgrades that massively enhance this discovery process. A real standout is the IP-level application convergence detection. This is a game-changer because it flags shared infrastructure blind spots. Imagine catching a hidden, unpatched internal tool, like an OnlyOffice instance, that just happens to be sharing an IP address with a totally public application. By connecting the dots on these overlapping nodes, WNCDS closes critical blind spots that your traditional single-target scanners just completely miss.
And there's a really brilliant technical nuance to how it builds this map. This system is actually smart enough to differentiate between types of wildcard responses. For example, it intentionally excludes catch-all CDN responses, like a CloudFront edge pool that's just throwing back rotating IPs for everything. You don't want that cluttering your map. But on the flip side, it keeps genuinely shared non-CDN virtual hosts, like a dedicated server hosting multiple distinct subdomains. This clever filtering prevents the map from exploding with false connections, while perfectly preserving the real, exploitable co-tenancy risks.
Moving right along to Section 2, the holographic fabric metaphor, or what we can call space-time security.
Okay, so with the attack surface meticulously mapped out, we transition to the actual engine protecting it all in real time. This is the SGI holographic fabric. The absolute most crucial point to grasp here is this physics metaphor. We are treating the network like a physical fabric. Just like the literal fabric of space-time warps under the stress of heavy mass, this digital fabric warps under the stress of an attacker traversing the network. If that stress becomes too great, the system doesn't just, fire off a Slack message to a tired analyst. It autonomously locks down. It turns to stone.
But how does the network actually feel that stress? Well, to measure this tension, every single cell continuously reads 3 distinct kernel telemetry signals using eBPF sensors. It's watching active network sockets, the number of running processes, and memory pressure. It takes these readings and establishes a healthy, authorized baseline. And look, the system expects a little bit of benign jitter, maybe a socket opening and closing, or a few bytes of memory shifting around. That's totally normal. That's just the network breathing.
Let's see how this works in practice in Section 3, tension, warp, and detection, focusing on island hopping the mesh. So how does this translate into real-time detection when a bad actor actually attempts to island hop across those weak nodes we mapped earlier? It all comes down to this number right here, 4.5. This is our warp_threshold. Using extremely fast, compiled C-speed math, the system continuously calculates the Euclidean distance between its healthy baseline and the current telemetry. 4.5 is the exact mathematical physical tension distance where the network triggers its autonomous lockdown response. To put that abstract math into perspective, think about standard background noise, like normal garbage collection in memory. That barely registers. It drops maybe a 0.5 distance score, staying well below our 4.5 limit. But now, imagine a reverse shell attack. Suddenly, you're adding 4 new sockets and 3 new processes. Boom! The Euclidean distance spikes to a 5.0. It immediately shatters the threshold, registers a structural warp, and throws the entire system into lockdown.
Now, if we zoom out from a single node and look at the entire mesh, it gets even cooler. As an attacker traverses the WNCDS map we made, their packets are injected as amplified perturbations into the SGI field. The system is constantly watching for a specific pattern. If a single source IP hits multiple weak nodes within a 30-second sliding window, it creates massive localized stress. The physical coherence of the network literally collapses under the weight of that island-hopping traversal.
Which brings us to Section 4, Autonomous Lockdown and Recovery. Turning to stone.
So, when that coherence collapses and the tension breaches our 4.5 threshold, the system hits a sudden, violent stop. This lockdown protocol is just brilliantly sequenced. First, it triggers real OS-level network isolation. It physically drops all network interfaces to stop the attacker's pivot dead in its tracks. Then it uses Raft consensus to broadcast a revocation of its own status to the rest of the mesh. Third, it wipes its spiffy cryptographic keys, so it literally can't forge messages to its peers, even if it wanted to. And finally, it enters a strict 30-second quarantine. It is completely isolated, turned to stone.
That lockdown is absolute. It gives the attacker zero room to maneuver. But what happens when that initial 30-second quarantine timer actually runs out, right? Because you obviously can't just leave production servers permanently isolated every time a threshold is breached.
Well, this is where the system's self-healing recovery sequence kicks in. The quarantine cell wakes up and remeasures its telemetry tension. If the attacker gave up and disconnected, and the state is normalized back below 4.5, it autonomously reinstates itself. It restores the network, resets its baseline, and gets right back to work. But if the warp remains, say if the attacker's reverse shell is stubbornly still running, it denies recovery and immediately locks right back down for another 30 seconds.
Okay, final section. Section 5, Proving the System Works, the engineering rigor.
A conceptual framework this ambitious, one relying on physics metaphors and autonomous isolation, absolutely requires extreme engineering to prove it belongs anywhere near a production environment. And I assure you, this isn't just some academic toy model. Look at the hardening involved here. It utilizes compiled C-speed math for high-frequency telemetry processing without causing lag. It features majority-based Raft consensus and SPIF-fee identities with SMHC SHA-256 signing. All of this ensures that even if a cell is entirely compromised by an attacker, it physically cannot trick the rest of the network or forge a fake all-clear message.
515. That is the exact number of passing automated tests validating this system today. You've got 82 tests just for the holographic fabric, 422 tests for the WNCDS mapping components, and 11 end-to-end integration tests locking in the reliability of the entire pipeline. The engineering rigor backing this up is just absolutely staggering.
And when they put this into live validation, the results totally speak for themselves. The system produced a 0% false positive rate over 20 benign trials. The SGI field creates what's known as a stable attractor, meaning it absorbs standard, everyday network noise perfectly without breaking a sweat. It only collapses when an actual malicious island-hopping traversal happens.
Honestly, what I love most about all of this is how the documentation ends with this powerfully honest scope statement. The engineers don't overclaim anything. They state very clearly, the system is a dynamical field that flawlessly detects island-hopping patterns, and it just honestly reports exactly what it measures. It doesn't rely on bloated signature files or constant cloud updates. It simply relies on the unshakable physical reality of the network state. Which leaves us with a really fascinating final thought to take away from this explainer. We've just seen how applying tension, warp, and physical coherence can completely revolutionize intrusion detection. So, how else could the physical laws of our universe inspire the future of cybersecurity? It really makes you look at a network not just as a bunch of code, but as a living, breathing physical fabric. Thanks for joining me on this deep dive. I'll see you in the next one.